Alright guys, this is our second podcast on stoichiometry, and what we're going to now do is apply our mole-to-mole relationships, specifically for grams, liters, and molecules. So, our last podcast was mole-to-moles, but what about grams and liters and molecules? Can you convert these to moles? Do you remember how to convert them back from moles? This was our last unit, not our last podcast, but back our last unit. This is exactly what we did, was we were talking about mole-to-mole relationships. So that's exactly what we're doing here. All right. So you must be able to convert names to symbols. All right. Remember all that? That's from a few units ago. You need to be able to balance chemical equations because we need balanced chemical equations to do stoichiometry. You need to be able to convert moles of substances to moles of a different substance. That's what we just did in our last podcast. And then we need to be able to convert moles to grams and liters and formula units, molecules, and back and forth. So those are all the pieces that are involved in stoichiometry. So let's look at this for a second. Let's look at an example. If you consume 6 moles of hydrogen, how many moles of oxygen are also consumed? Well, this is what we just did in our last podcast. So we're looking at how many moles of hydrogen we have and how many moles of oxygen we have. So we start with 6 moles of hydrogen, and we multiply. We get rid of our moles of hydrogen, get rid of our moles of hydrogen down there and go to moles of oxygen, and we end up with 3 moles of oxygen. That's what we did in our last podcast. So what we did was we converted from moles of our starting substance to moles of our ending substance. Okay? So it didn't matter whether we were dealing with reactants or products. We looked at what we were given in the problem, and we started with the information we were given in the problem. That's our starting substance. And we tried to get to moles of whatever our target substance was. So that's what we did in our previous podcast. But most problems are not mole-to-mole problems. After all, before you came to chemistry, did anyone mention mole-to-mole problems to you? Of course not. Let's say you were mixing concrete. They'd say, well, you have this many pounds of sand plus this many pounds of gravel. How many pounds of concrete do you have? Or even worse, what's the volume of the concrete? Are you making chocolate chip cookies and you're taking 2 eggs and you're taking 2/3 of a cup of white sugar and 2/3 of a cup of brown sugar and 12 ounces of chocolate chips and all of these different things mixed together, right? That's exactly what stoichiometry is all about. Because if most problems are not mole-to-mole problems, what good is stoichiometry? You have to convert everything to moles before you can solve it, right? You must make every problem into a mole-to-mole problem. So if it's not a mole-to-mole problem, you must make it into one first. And you must convert things into moles, and then you must convert things from moles. So the easiest way to do this is give you some examples, right? But you need to remember your conversion rules. Your conversion rules are that 1 mole is 22.4 liters of a gas, of any gas at standard temperature and pressure. 1 mole is 6.02 times 10 to the 23rd things, and 1 mole is some number of grams. Yes, you guys know that, all right? So if you look at this carefully, you'll notice that down in here, this is the stoichiometry piece that we did in our previous podcast. And all of this other stuff, all of this superfluous stuff around it, that's getting 2 moles. So if I gave you grams of a particular substance, and I said, how many grams of my target substance would you end up with? Well, you can't go directly from grams. You have to go from grams of what you started with to moles, and then do what we did in our previous podcast, and then go up to grams of my target substance. Or I could go to liters of my target substance, or even molecules of my target substance. So that's kind of your flow chart that we're going to be working from. There's one of these. It's a little bit more complicated in your packet, but let's go and do some examples so that you can understand what we're doing. All right. If I consume 6 liters of oxygen, how many grams of water are produced? So up here I have 6 liters of oxygen, and I'm saying how many grams of water are produced. All right, so let's think just for a second of what I have to do. I have to go from liters of oxygen to moles of oxygen because I want to use my coefficients, which are 1 and 2, to be able to convert from moles of oxygen to moles of water, and then I can go to grams of water. Let's write that down. All right, so I'm starting with liters of O2, and I want to go from liters of O2 to moles of O2. And then from moles of O2, I want to go to moles of water. And then from moles of water, I want to go to grams of water. All right, let's look back at our previous slide and see what that means here. Right. I'm starting with liters of water. And liters of oxygen. And I'm trying to go to grams of water. So look at my path as I do that. I go from here to moles of oxygen to moles of water, and then to grams of water. So that's what we're going to do in this to solve this problem. So let's go ahead and do this. We start with 6.0 liters of oxygen. Now remember, you have to write down all of your units, right, to be able to do this. So I have 6.0 liters of oxygen, and that means I have to get rid of liters of oxygen, and I'm going to go to moles of oxygen. Now you'll notice this, what I wrote right here, this thing, that's helping guide me as I go through this process, so I don't get lost. So I'm trying to go to moles of oxygen, but I don't want moles of oxygen, so I get rid of moles of oxygen, and I go to moles of water. But I don't want moles of water. I have to get rid of moles of water, and I have to go to grams of water. All right. So now, if I cancel all my units, I'll end up with grams of water, which is what the problem is calling for. So what are my conversion factors? Well, I know that every 1 mole of oxygen gives me 22.4 liters of oxygen. And if I look at my relationship between moles of water and moles of oxygen right here, well, that's what we did in our previous podcast, and 1 mole of oxygen gives me 2 moles of water. 1 mole of oxygen gives me 2 moles of water. Now, how about moles of water to grams of water? Well, 1 mole of water weighs, well, we have to figure out what oxygen water weighs, and you can do that. That's 18.015 grams. And I'm going to actually do all the math. So I take 6, I divide by 22.4, I multiply by 2, I multiply by 18.015, and I come up with 9.7 grams of water. You'll notice I only have 2 sig figs in my answer because I only have 2 sig figs in my problem. All right. Hopefully that helps you understand what you're doing. So why don't you pause the video and see if you can do this. We're going to go through 4 examples. Right? And the more that you can do on your own, the better prepared you're going to be. All right. How many liters of carbon dioxide is produced? So I'm looking for liters of carbon dioxide produced from 36 grams of glucose. 36 grams of glucose. That means I have to figure out how much glucose weighs to be able to do this, because I want to go from grams of glucose, C6H12O6, and I want to go to, what do I have to do? I have to go to moles, because I need to use the 1 that's out here. I need to go from moles of glucose, C6H12O6, to moles of CO2, that's CO2, and then from there I go to liters of CO2. All right, so let's go ahead and try this. That means I need to figure out how much C6H12O6 weighs. And by the way, if you figure that out, that's 180 grams per mole. So I'm not going to waste your time doing that here. So we start with the information we're given, which is 36 grams of glucose. And we have to go through this long process of getting rid of grams of glucose, H12O6, to moles of glucose, and then from moles of glucose to moles of, well, my target is carbon dioxide, so it's moles of carbon dioxide. And then I go from moles of carbon dioxide to liters of carbon dioxide. Okay, so what ones can I do? Well, I know that 1 mole of glucose weighs 180 grams. And I can see that I have, for every mole of glucose I produce 6 moles of water. And every mole of water, I get 22.4 liters. So if I take 36, divide by 180, multiply by 6, and then multiply by 22.4, I get 27 liters of CO2. Okay, let's do another one. Again, we're going to use the same equation, right? Just because that should make it a little bit easier for you. Go ahead and try this, see if you can do it. All right. Well, I'm still going from 36 grams of glucose, so I have 36 grams of glucose, and now I'm going to grams of water. So nothing else matters in my equation. All that matters is that I'm going from glucose to water, and I have a relationship of 1 mole to 6 moles. So let's go ahead and start the problem and see where I go. 36 grams of glucose, C6H12O6, and I have to get rid of grams of glucose, and I have to go to moles of glucose. That's exactly what we did last time. And now we go from moles of glucose to moles of water, because we want to go to water this time. And then we have to go from moles of water to grams of water. All right, and that's where I want to end, because that's my final target. So let's see, we have 180 grams of glucose in 1 mole. We just did that. We have 1 mole of glucose to 6 moles of water. And 1 mole of water weighs, well, you have to figure out how much water weighs, and that's 18.015 grams. So when you actually multiply across the top and divide by everything on the bottom, you get 22 grams of water. All right, let's try another one. Right. See if you can figure this out, write down what you need, and go from there. Okay? Pause the video, try it on your own. Alright, I am trying to figure out molecules of glucose. Molecules. And I have 52 liters of oxygen. 52 liters of oxygen. Well, you notice they're both on the same side. That doesn't matter. It makes absolutely no difference. So, you're trying to go from liters of oxygen. So to get to where I want to get to, I have to go from liters of oxygen. Remember, you're always converting to moles. You're going to moles of oxygen. And then from moles of oxygen, you're going to moles of glucose. And then from moles of glucose, you're going to molecules of glucose. All right, so let's go and start with what we have. All right, if you couldn't get that far, pause the video, see if you can do the math on your own. All right, so we start with 52 liters of oxygen. And we want to get rid of liters of oxygen and go to moles of oxygen. And from moles of oxygen, you'll notice I'm just following my little thing up here. It tells me how to go. Moles of oxygen, I'm going to moles of sugar, C6H12O6. And from moles of sugar, I'm going to molecules of sugar. All right, so what conversion factors do I know? We're assuming we're working at STP, so 1 mole of oxygen is 22.4 liters. And 6 moles of oxygen gives us 1 mole of glucose. And 1 mole of glucose, molecules, what number is that? Oh yeah, that's Avogadro's number. That's 6.02 times 10 to the 23rd molecules of glucose. So if I multiply across the top, divide by everything on the bottom, I will get 2.3 times 10 to the 23rd molecules of glucose. Okay, so that's that one. All right, we have one more problem we're going to do. Right? And this is going to be the one where you put it all together. So, how do airbags work, folks? Well, in a car, airbags contain something called sodium azide. And the question is going to be, what volume of nitrogen gas is produced from the decomposition of 125 grams of sodium azide into sodium and nitrogen? Well, this actually would be a real problem because you have to make sure you put the right amount of stuff in there so when the airbag deploys, it doesn't explode, or it doesn't just kind of fizzle and not give you enough nitrogen in the bag. So the first thing you have to do is what? Sure, you have to produce a balanced chemical equation. So number one, do a balanced chemical equation, and then stop, pause the video, write down the balanced chemical equation, and then come back. Alright, this is clearly a decomposition reaction, and you have Na, N3, and it's decomposing into sodium, which is Na, and nitrogen. And nitrogen is a Brinkelhoff element, so it's N2. And now you notice you have N2 on the right and N3 on the left, so we have to do our sixth thing. So that's 6 nitrogens now, which means I need 2 sodiums. Right, that's my balanced chemical equation. Did you get there? Alright, well now that you have this, you should be able to go and start with your 125 grams of sodium azide and work your way through the problem. So, pause the video, see if you can do that on your own. Alright, so we have 125 grams of sodium azide, and we're trying to figure out how many liters, because we're looking for volume, how many liters of nitrogen gas we have. Alright, so let's go ahead and do this. We start with 125 grams of sodium azide, NaN3, and what do we have to do? Well, we have to go from grams of sodium azide to moles of sodium azide, and then we have to go to moles of N2, and then we have to go to liters of N2. All right, so let's go ahead and do that. We have to go from grams of sodium azide, NaN3, to moles of NaN3. Then we go from moles of NaN3 to moles of N2. And then we go from moles of N2 to liters of N2. I got mole happy there. Alright, so let's see. 1 mole of sodium azide weighs, oops, I've got to figure out how much that is. Well, if you add up sodium, which is 22.99, and 3 nitrogens, which are each 14.007, you come up with 65, goes down here, 65.011 grams of sodium azide. Now, what's my relationship of sodium azide to nitrogen? Well, it's 2 to 3. That's a 2. That's a 3. And I'm trying to go from moles of nitrogen to liters of nitrogen, and that's 22.4. Right, so I multiply across the top, divide by everything on the bottom, and I get 64.6 liters of N2. So folks, that's it. Clearly you have to plan how you work through this so that you solve every problem, but remember, everything has to go to moles before you can go to something else. So it's now your turn. Go ahead and give it a shot. Try it. Ask for help if you need it, and you know where to find us. Okay, we'll see you in class. Have a good one. Bye-bye.